All right, let me tell you a little bit about massive star evolution. And this is for stars of greater than about 8 solar masses. Um, Here's what happens. Remember what happens in small stars. It stops whenever there is carbon in the core because it doesn't get hot enough to fuse carbon. Massive stars can crush the core so that the temperature gets driven above 600 million degrees or so. And so then you can fuse carbon. What happens first, a lot of times, is that the carbon that's down in the core starts fusing with some of the helium that's around there. Remember that helium reaction is kind of rare because you need 3 heliums to all collide in the same place, which is a pretty rare occurrence. So there's plenty of other helium nuclei just floating around. So it's hot enough so that some of these can combine with the carbon. And what do you get? Let's see. Carbon, well, you have 12 particles in the nucleus plus 4 particles, so you're going to get something with 16 particles in the nucleus, right? If I just add those numbers together. Carbon has 6 protons, helium has 2 protons. So naively, you would expect 6 plus 2, 8, an element with 8 protons. What element has 8 protons? It would be oxygen. This is where oxygen comes from. Very cool. The oxygen that we breathe originally had its birth. Those oxygen atoms originally were manufactured in the cores of gigantic stars billions of years ago. Very, very cool. This is one reaction that can happen. Here's another one. The deal is that once you can fuse carbon, everything else just sort of rolls downhill. Getting carbon to fuse is the big roadblock. Once carbon starts fusing, then everything else follows in line. So very quickly, faster and faster, once you burn up all the carbon in the core, now the core is mostly oxygen, right? So now the oxygen combines with the helium. And what you get, if you look on the periodic table, 2 more protons gives you neon, element number 10. And then neon can combine with helium to form, if you look this one up, that one is magnesium. And so on. Each time in the core, you produce a new element, and then it's a shorter and shorter period of time until that element runs out. And so the star sort of furiously tries to find something else to burn. Because remember what's also happening is that the star is trying to find something to burn to push out, because what's countering that always is gravity trying to crush the star. The star is basically the same amount of mass. The gravitational force is always the same. So as soon as it runs out of one source of fuel, it better find another one, or else gravity is just going to crush the thing. So it's sort of a more and more desperate fight to find things to burn to keep itself inflated. So you can do magnesium. Also around this time, you can do this. Carbon plus carbon. Carbon can find other carbon to fuse with in a shell. And so again, you get magnesium and so on. And so you can keep burning these things. And what you get ultimately is that you can fuse your way up the periodic table until you get to iron. And once there's iron in the core, the star is doomed. It doesn't know it yet, but the star is doomed. But so the structure kind of looks interesting. So you have these are gigantic blue stars, right? Okay, so this is just an idea of what the core looks like. So in the core of the star, you have one layer that's burning one thing. There's a really nice drawing. There's a nice illustration in the book. And then there's another layer, and then there's another layer, and then there's another layer. And then finally, at the center, you get iron. So maybe this layer out here is oxygen burning, and then this one might be neon burning and magnesium, and maybe that one is silicon or whatever. So anyway, the idea is that you have these different layers of different kinds of burning that's going on. And then eventually at the very center, you get iron. And once you get iron, you're done. The reason is because iron will not fuse. It doesn't matter how high the temperature gets. It doesn't matter how much you crush it. It turns out that iron is the most tightly bound of all the atomic nuclei. You can't squeeze anything into iron. You can't fuse anything with it that will give you energy. It just takes energy. So iron will not fuse. So what happens is once the star starts building up a core of iron, you lose anything that withstands gravity from it, right? There's nothing pushing back out. So once the core starts building up, the star starts slowly and then faster and faster, it'll start to collapse. And then more and more iron is being made further out as the star gets more and more desperate, and then all that iron starts raining down on the core. And what happens is that the star implodes, the star collapses, and when it collapses, there's sort of a rebound where the star then explodes as a supernova. This is another way that you can get a supernova. Remember the one we talked about before was from a white dwarf? This kind of supernova comes from the collapse of a massive star. This one we call a type 2. It's a little bit backwards, I guess. Type 2 comes from the collapse of one massive star. A type 1 comes from a white dwarf in a binary system, so from kind of 2 stars. Anyway, so this is a supernova type 2. They generally tend to be a little bit less bright than type 1s. There's a number of reasons for that. Sometimes these massive stars give off, they lose a lot of mass in their outer layers, and so whenever this thing goes off, there might be sort of an envelope of gas that it has to fight through, and that kind of dims it. But anyway, type 1s usually are anywhere from 5 to 10, something like that, 5 to 10 times brighter than type 2s. But this is what you get. Massive stars will collapse and form a type 2 supernova. And notice all of these new elements that they generate, all the oxygen, neon, magnesium, silicon, and so on, all this stuff is spewed out into the interstellar medium. And what that does over billions of years is it collects back together slowly and forms new generations of stars. And now the new generations of stars have been enriched with this new carbon, oxygen, neon, magnesium, and so on. So this is where the elements come from that make up things like planets and people and so on. So it probably wasn't possible to have life in the universe or rocky planets until a few generations of stars went by to sort of cook the soup, right? To enrich the soup a little bit, to get a nice mix of heavy elements in there that the stars generate. Because what surprised people, and we'll talk about this in the next couple of weeks, is that you might imagine, well, maybe the Big Bang was so hot and dense, the Big Bang maybe was like a gigantic star itself. And so maybe all the elements in the periodic table were cooked up in the Big Bang. But for reasons that we'll talk about, which was kind of surprising to people once we did the calculations, that's not what happened. The Big Bang only made basically 2 things, hydrogen and helium, and that's it. Just a smattering of other things like lithium and so on. But basically only hydrogen and helium. The universe had to wait a long time until stars came along to cook up all the other elements. It's still, I'm going to leave it as a little bit of a mystery until we talk about compact objects. So far, this is where all the elements up to iron came from. But we know that there are elements on the periodic table past iron. There are things like gold, silver, things you wear as jewelry around your neck, lead, right, uranium. All of those, where did those come from? Because apparently you can't make those from fusion. So those are an additional puzzle that we'll talk about as we get there. Have we ever seen anything like a Type 2 supernova? On the class page, I just loaded up a picture of a Type 1 viewed from far away around a neighboring galaxy. That's supernova 1994. type 2s, we have seen them. Supernova 1987 that went off, that we'll talk about next time. That was a type 2. That was one single massive star that collapsed and exploded. And have we ever seen this happen live? Yes. Not us. But back in history, the Chinese saw it in the year 1054, and other cultures around the world, the Indians and southwestern United States, saw what they called a guest star up in the heavens. And it turned out to be a massive star that collapsed and exploded. And when they wrote about it, they said that you could see it in the daytime, and it outshone the full moon. You could read by it at night. So it was terrifically bright, and then it just dims over the course of 2 to 3 weeks and kind of goes away. And now when we turn a telescope to the point in the sky where they said that this happened, almost exactly 1,000 years ago, we see this. Now we call this the Crab Nebula. And this is a supernova remnant. All of these layers, we can tell by the Doppler shift of the lines that all of these layers are rushing out. So we're looking at an explosion 1,000 years after it happened. All of these gases are rushing away from a central point. And this is the result of the supernova that happened just about 1,000 years ago. Very cool. So we've only seen a handful. I think there was a supernova seen in like 1604, Kepler's supernova. 1987, in the southern hemisphere, we saw one. This was in 1054. There's only been a handful in recorded human history that we've actually seen live. It's a very, very rare event. So let's just say a word or two, because now we can say something kind of interesting about the way that the universe is organized. This is a plot of all the elements on the periodic table and how abundant they are. The higher up on the plot, then the more abundant it is. You could probably guess. I think there's a table in the book that represents all this stuff. You could probably guess that up here, let's see, I better choose a color that shows up. There's hydrogen. And I also put this plot on the class Moodle page so you can see it for yourself. There's hydrogen. It's the highest on the plot, which means it's the most abundant. Here, look. It says the log of the abundance. And if you don't remember your logarithms from whenever you saw logarithms, high school, or whatever, it's not a big deal. All it means is that every tick on the right-hand side is actually a factor of 10. So, like, look at helium. Helium goes from, like, what, 9.5, and hydrogen is up at, like, 10.5 on the y-axis. Since they differ by 1, what that really means is that the real abundance is different by like a factor of 10. So logarithms just sort of shrink the y-axis. So this is telling us that hydrogen is like 10 times more abundant than helium. In fact, hydrogen happens to be like 90% of the entire universe. Helium is like 8% of the entire universe. So hydrogen and helium are the two most abundant things in the universe. So there's I'll just keep this color, most abundant. Looks like hydrogen and helium are the two most abundant. And then you look down the chart. What's the next most abundant? I don't know, kind of to me looks like maybe oxygen. You can check the table in the book, so maybe I'll get these a little bit different, but I think this is right. Oxygen, and then if I'm just sort of looking at it by eye, it looks like there's maybe carbon, nitrogen. I think I asked you in the objectives to know the top 6. So it's hydrogen, helium, oxygen, carbon, nitrogen, and then what's next? Could it be neon or could it be iron? I don't know. If you say either one, I don't care. Anyway, something like that. So these are the most abundant elements in the universe. So let's just talk. This is a really interesting plot. Let's look at this for a second. Just generally, can you say anything generally just looking at these elements? What elements in the periodic table are the most abundant? Well, generally, if I were to just sort of eyeball the plot, the lighter the element, the more abundant it is. We kind of know that, right? They're easier to make. Stars start off, apparently the universe started off with hydrogen and helium and built the rest of the elements from there. So it kind of makes sense that the lighter elements are going to be more abundant. But there's an exception. Look at these. Look at those down there. Lithium, beryllium, and boron. Those are, and remember, each tick is like a factor of 10. So those elements are like, what, factor of 100 million times, almost a billion times. Beryllium is almost a billion times less abundant than hydrogen and helium. Why is that? Why are lithium elements 3, 4, and 5, why are they not very abundant? Well, we know the answer to that. Remember last time, why that would be is because stars can't make them. Remember how small star fusion works. You go right from helium to carbon. You have to combine 3 heliums to make a carbon. So stars completely skip over that. Stars don't make lithium, beryllium, and boron. Since stars can't make it, nothing else in the universe generates elements like that, at least not much. So they are not very abundant. You might wonder why there's any at all. And that answer is a little more complicated. You can make them with cosmic rays and radioactive decay and so on, but it's not easy. Stars don't do it. So they are not very abundant. So once you get back up here to carbon, that's something that stars can make pretty easily. So it tends to be pretty abundant. So now we know that was originally kind of a mystery. Why are lithium, beryllium, and boron not very abundant in the universe? Well, once we developed a theory of how stars work, now we can answer it, because stars don't make it. Carbon, and here's another pattern. Look how it bounces around from one element to another. There's carbon, and then nitrogen is almost a factor of 10 less abundant. And then we bounce up to oxygen, and then down to fluorine, and then up to neon, down to sodium, up to, that's not labeled, but it's magnesium. Anyway, there's this sawtooth pattern. It looks like the most abundant elements are even-numbered elements. Carbon, oxygen, neon, magnesium, silicon, those are all elements that have an even number of protons. Well, that's interesting. Why are the even-numbered elements a lot more, 10 to 100 times more abundant than the odd-numbered elements? Well, we know the answer to that too now, because in massive stars, wherever you make these heavier elements, how do you make them? You're adding a helium each time. You don't add a hydrogen. Hydrogen is pretty much gone when you get to the very center of the star, but helium is still around, and so those different fusion avenues, you generally keep adding. Let's go back to it. You generally keep adding helium, which is 2 protons. So each time one of these steps in the periodic table is made, in the fusion cycle, you go up 2 in the periodic table. So now we can answer that too, if that was a little bit of a mystery. Why are the even-numbered elements more abundant? It's because each time stars make them, they tend to add a helium, and so you leapfrog the odd-numbered element. Very cool. There's a couple of others. How about this? Well, look at that. Look at iron. Iron is like 100 times more abundant than you might expect than its neighbors. Why is there a peak there around iron? We kind of know the answer to that too, because that's the end result of fusion, right? All the elements sort of pile up there at the end of the fusion cycle, because fusion stops with iron, so iron kind of builds up. So it's not surprising that we have sort of a peak there at iron. Here's another one that you might remember. Pb, that's lead. Why is there sort of a spike where lead is? If you remember, that's because lead is sort of the ultimate result of all radioactive decay. All of these elements, like uranium and thorium, all decay to lead. So over the course of time, lead sort of builds up, because lead is the most, it's the heaviest stable element. Everything heavier than lead is radioactive and will decay back down, mostly to lead. So lead kind of builds up. So anyway, all I'm saying is our modern theory about how atomic nuclei behave and fuse, especially in stars, can account for this plot. We can explain this plot. And any good theory of how the universe works, had better be able to explain the little ups and downs and the general behavior of these plots. And now we can do it with our theory, stellar evolution. Okay, like I said, we haven't really talked about all of those elements and where they came from yet, but we will, because what we haven't talked about yet, now that there's been a supernova explosion, a type 2 supernova explosion, I haven't told you yet what's left behind. What happened to that iron core that collapsed? It's a really interesting story, so that's what's coming next.